Okay, so our video here is going to be about how second order differential equations can be used to model spring motion. We are only going to be looking at undamped systems here and how it ties into Newtonian mechanics. So let's just suppose that you have a flexible spring and it's suspended vertically from a support system and you put a mass onto the free end. The amount of stretch, or how much that mass pulls on the spring, is of course going to depend on the mass itself. Now, unstretched, it's just going to sit here. The mass is going to put some kind of stretch on that. And then once it sits here in this equilibrium position, that means that the mass and gravity must be equal to whatever the spring constant is. We're going to call that K. Okay, this proportionality constant, times that S piece right here. Okay, so that's kind of like the opposing force, if you will, so that it just sits in equilibrium. Now, we might put this spring into motion by kind of like pulling it down and then letting it go. We'll talk about that here in just a minute, but I want to make sure that you understand that when you put that mass on there and just leave it alone, you are now in that equilibrium position. And so that force must be the same going down as going up. So that's a summary with a picture of all of this piece right here. And so this is what must be true. Mass times gravity, okay, and we're going to be doing this in feet and seconds, okay, so US units here. So gravity is 32 feet per second, whatever your mass is, okay, is balanced out by that restoring force, KS. So you want to make sure, since gravity is in feet per second, that your S is also in feet. And so if you look here, our first kind of example as we step through this problem is using this information. If a mass weighs 10 pounds and stretches the spring by half a foot, then what's that value of K? So you put that mass of 10 pounds on here, and then it goes half a foot. So S is half, so M is 10 pounds, S is half. We're using that gravity is 32, and so what's the value of K? So you can use either one of these. I prefer this equals, so 10 times 32 equals K times a half. This would be 320, and so K must be 640. Now that's based on like that spring constant, like what is K? That spring constant is based on the materials that are used for that spring, how tightly the spring is stretched. So if you think of like a slinky, the material used on a slinky is usually not like a metal slinky, is usually pretty bendy, okay? It's pretty malleable so that the spring can bend. It's pretty thin. And usually a slinky that actually like can go like a good old school slinky, that could like move on stairs and things like that, is going to be not wound very tightly, okay? Whereas when you think of like springs that hold up the Fred Hartman Bridge, let's just say, okay, the bridge here in Houston, those are going to be tightly wound and made with material that can hold up a bridge, okay? So that's what that K is it's relative to the spring, the materials and everything that it's made out of. So that K is true for that spring. So how far would an 8-pound weight stretch that same spring? So I'm going to do 8 times 32. I know my spring constant, and now I want to find S. So 8 times 32 is 256. I'm going to divide by 640. and I get 0.4. Now remember that's in feet. Okay, we don't worry about having units with our spring constant, but S is going to be in feet. And if I wanted to then multiply that by 12, I could figure out the inches, 4.8 inches. Okay. All right, so now our next part is we're going to be going into motion. This is really interesting, okay? So kind of wrap your brain around this for a second. When we go to put this spring in motion, so now I'm talking about like this third piece here, because you are making the spring longer, when you pull the weight down, we're actually going to call that positive X. And I know like on your Y axis, right? Usually this is positive Y and this is negative Y, but don't think about it that way. You want to think about this as like you have a positive displacement, or you're making the spring longer. And so this is your positive. And if you were to actually push, instead of like pulling it down, if you were to take the spring and push it in, okay, with some force and then let it go, then that would also end up putting the spring in motion. But then you would be making the spring smaller. So your initial value for your X, for your displacement, would be negative. So let's look at setting this into motion. Okay, and what might happen here. So when you're in equilibrium, we're going to say that's X equals 0, okay? And then displacement measured below equilibrium is going to be a positive displacement. So let's say that you elongate the spring 4 inches from equilibrium. Let's see, 4 inches, 4 over 12, that's 1/3 of a foot. And then you just release it. So let's graph kind of what's going on here. You have your spring, right? Here's equilibrium position. You pull the spring down 1/3 of a foot, and then let's think about what happens. You just let it go. So it goes up, right? Because you're here, because you pulled it down. It's going to go up, and then it's going to come back down. And then assuming, of course, that there's like no wind or anything like that. Okay, just we're going to call it's called free motion. It's just letting it go. Okay, that weight times gravity is always going to pull it down, and then we're going to have that restorative force that pulls it back up. So if you think about what this graph of the displacement would be, you're going to end up having that displacement X starts at positive 1/3, right? X of 0 is positive 1/3 of a foot. It just so happens, because of that equal mass times gravity, K times S, okay, when you're here at equilibrium, that it's going to go down to negative 1/3. Like that's going to be equal there. And then it says it takes 2 seconds to return back to its starting position. So this must be 1 second then. And then at 2 seconds, it's back here. And so that displacement is going to look like this. And if you know your parent functions, you should see that that's a cosine function, cosine of t. Now there are some like theoretical reasons as to what we're going to set up next. Just kind of stick with me as I overview this. So Newton's second law of motion is that the sum of the forces is mass times acceleration. And so we end up having acceleration is the second derivative of position. And so if you do those things, okay, and then there's some algebra here, you get that mass times acceleration is equal to negative K times X. Okay, so K times wherever the position is at any point in time. And that's like a negative relationship there. If we solve that in a linear way, standard form, and divide everything through by m, bringing kx over first, okay, I didn't show that here in the notes, but if we bring kx over first, so we make this a homogeneous equation, and then divide through by m, you get this. Now we call this omega squared is your km, or k over m. And so this is going to be a second order differential equation written in linear form. And notice it's a lot like when we've done these problems like this, okay? Like y double prime plus 16y equals 0, which gave us sines and cosines, right? That should kind of make some connections here. All right, so let's talk about how we're going to figure out the actual equation for this, okay? Let's go back up and see what we had here. So it started at, what was our k value again? K was 640. We need that. Okay, and we're going to use the very original mass, okay, mass of 10. We put it into motion by saying x of 0. It was pulled down by a third. Now, it was just released, right? Like I didn't push it in any way. So my velocity at 0, or x prime at 0, must be 0 because I just let it go. Now, really quickly, if I were to push it up, okay, then that's actually like negative, like pushing it up is a negative term because you're making displacement of the spring shorter, so its change would be negative. If you take it to that place and then push it down, that initial velocity would be positive, okay, because you're making the spring longer. So just some ideas there, but in this one, we just have a release, which is nice, so it's 0. Okay, let's figure out omega squared. So omega squared is k over 10, which is 64. So I know that x double prime plus 64x equals 0. And the square root of 64 is 8. So that means that my x of t must be C1 cosine 8t plus C2 sine 8t. I know that 1/3 is my output at time 0. So C1 must be 1/3. And then I know my initial velocity is 0. So if I take x prime, plug that in, I end up getting that C2 has to be 0. Okay. And so I end up that my position equation must be 1/3 cosine 8t. And that's my final answer.